So before we dive into what ReLu, Sigmoid, or Tanh actually do, let's first understand why we even need activation functions in the first place. Imagine we build a neural network, but we don't use any activation functions. Every neuron just multiplies inputs by weights and adds them up. That's completely linear math. And here's a catch. If you stack multiple linear layers on top of each other, the result is still just another linear function. No matter how many layers you add, the model can only learn straight line relationships. Let's take a look at a simple linear example to make that clear. Say we want to build a small model that converts US dollars to euros. If the exchange rate is about 1 US dollar is equal to 0.95 euros, then 10 US dollars is equal to 9.5 euros, 100 US dollars is equal to 95 euros. That's perfectly linear. If you double the dollars, you double the euros. The rule is just y is equal to 0.95 times x. For a relationship like this, you don't need activation functions. A simple linear model can learn that conversion perfectly because the pattern is just a straight line. Now let's compare that to something much more realistic and much less linear. Imagine you're building a model to predict whether a customer will stop using your streaming service. You might have inputs like this: how many hours they watched last month, how long they've been subscribed, whether they contacted support recently, and their age. Here's the tricky part. Someone watching very few hours might be likely to churn. Someone watching a moderate amount probably stays. But someone watching 20 hours a day might churn too. There's no straight line you can draw through that data. And that's where activation functions come in. By introducing nonlinearity, activation functions let the network bend and twist its decision boundaries. Now, instead of drawing straight lines through your data, it can form curves that actually fit the real world patterns. So in short, activation functions are what make neural networks powerful. They're the reason a network can go beyond just math equations and start learning patterns. This is ultimately the foundation of what we call deep learning. Now let's talk about the sigmoid function, one of the simplest and most classic activation functions. It takes any number and squashes it between 0 and 1. So large positive inputs get close to 1, large negative ones drop towards 0. That's why it's often used when we want an output that represents a probability. To make this easier to picture, think of a single neuron as a bouncer at a club. The bouncer's job is to decide whether to let someone in, output a 1, or keep them out, output a 0. But instead of making a yes-no snappy decision, this bouncer uses the sigmoid rule, a smooth curve that turns any score into a probability between 0 and 1. Step 1. Let's say a person walks to the line and wants to get in. The bouncer looks at two inputs about the person in line. Input 1. Are they a VIP? 1 for yes, 0 for no. Input 2. Are they wearing flip-flops? 1 for yes, 0 for no. Let's say a person walks up who is a VIP and is wearing flip-flops. Step 2. The bouncer has their own internal weight, W, for how much they care about each fact. A VIP status is very important, so the first weight is equal to positive 5, but the bouncer hates flip-flops, so the second weight is equal to negative 10. Step 3. Add in the bias. The club isn't very busy tonight, so he's a bit more lenient. Bias is equal to positive 2. The bouncer now calculates a total raw score represented by Z by adding up all the weighted inputs and the bias. Input 1 times weight 1, input 2 times weight 2. We add the result of these two along with our bias and get our raw score denoted by Z. Step 5. He can't just shout -3 at the person, he has to make a final decision. His rule is the sigmoid activation function, which will squash the score into a probability. Plugging it in gives, so the approximate final output is 0.047, or 4.7%. That means there's only a 4.7 chance this person gets in. Even though they are a VIP, the hatred for flip-flops outweighed everything. The bouncer/neuron outputs a no. That's the sigmoid function in action. It turns raw scores into probabilities that guide decisions. But notice those flat edges of the curve. That's where learning slows down because the gradient becomes tiny. That's the vanishing gradient problem. And it's why we moved on to better functions like ReLu. Now let's talk about one of the most popular activation functions in modern neural networks, the ReLu, or Rectified Linear Unit. While sigmoid squashes values between 0 and 1, ReLu takes a different approach. It simply says, if the input is positive, let it pass through. If it's negative, shut it off. Mathematically, that's the simplest rule possible. To make this easier to picture, let's walk through an example. Think of this neuron as a dimmer switch for a light bulb. Its job isn't to make a yes or no decision like the club bouncer from before. Instead, it decides how bright the light should be, but with one hard rule. There's no such thing as negative brightness. So if the signal coming in is positive, the light turns on. If it's negative, the light stays off. This is ReLu in a nutshell. Step 1. The dimmer switch gets two input signals. Input 1 is the brighten button. Think of this as the button you press when you want more light. It's meant to increase brightness, which in our case is pressed, so that will be denoted by 1. Input 2 is the dim button. This is the button you press when you want less light, which is also pressed, so another 1. Step 2. Each button has a different weight, representing its strength in the circuit. The brighten button is powerful. The weight is equal to +8. When this button is pressed, it sends a strong signal to the dimmer switch saying increase the brightness significantly. The dim button weakens the signal. Its weight is equal to -3. When this button is pressed, it sends a signal to the dimmer switch saying decrease the brightness a bit. Step 3. Add the bias. Even when nothing's pressed, the system has a small negative bias, a standby draw of -1. Now the neuron calculates the total electrical signal, Z, being sent to the dimmer before the rule is applied. Input 1 times weight 1, input 2 times weight 2. We add the result of these two along with our bias and get a raw score denoted by Z. Step 5. Apply the ReLu rule. It checks, is my input greater than 0? Since Z is equal to 4, ReLu outputs 4. The light bulb turns on, shining with brightness 4. Positive signals pass right through untouched. But what if the input goes the other way? Let's say only the dim button is pressed. So now instead of multiplying our 8 by 1, we will be multiplying 8 by 0. Now the ReLu rule kicks in again. We take the max between 0 and -4. And since 0 is higher than -4, we get 0. This means the light shuts off completely. No negative output, just 0. That's the ReLu magic. It kills off the negative signals and lets positive ones shine. This simple hinge behavior makes ReLu incredibly efficient. It's fast to compute, avoids the vanishing gradient problem, and allows deep networks to learn complex patterns. That's why ReLu became the default activation function in most modern neural networks. But it's not perfect. If too many inputs go negative, those neurons can get stuck outputting 0 forever. That's what we call the dead ReLu problem. To fix this, researchers came up with variants like leaky ReLu, parametric ReLu, and ELu, which allow a tiny negative slope instead of cutting it off completely. Now that we've seen how ReLu powers modern networks, let's talk about another important activation, the tanh function, short for hyperbolic tangent. Tanh is like the middle ground between sigmoid and ReLu. It's smooth like sigmoid, but it outputs values between -1 and +1. So instead of off or on, it gives balanced signals that can be positive or negative. This range makes tanh special because it centers its outputs around 0. That means neurons can express both excitement positive and inhibition negative, making learning faster and more stable. To make this easier to picture, think of this neuron as a thermostat in a smart home system. Its job isn't to turn the heater on or off, it needs to balance between heating and cooling to keep the temperature just right. That's what the tanh function does. It lets the neuron think in both directions, warming things up, positive output, or cooling things down, negative output. Step 1. The thermostat gets two input signals. The first input is the heater level, which we will set to 1. The second input is the cooler level, which is also set to 1. Step 2. Each input has a weight showing how strongly it affects temperature. The heater has a strong influence. Its weight is equal to +6. The cooler fights against this. Its weight is equal to -4. Step 3. Add the bias. This represents the thermostat's default offset. Maybe the room tends to run a bit warm, so the bias is -1. Now we calculate the raw signal, Z. Step 4. Apply the tanh rule. Mathematically, tanh of Z is equal to, plug in Z for 1 and you get about 0.76. That means the thermostat outputs a signal that's mostly positive, telling the system to heat up, but not to the max. It's staying balanced, not blasting heat, not freezing either. Now imagine the cooler kicks in harder. Applying tanh again, tanh of -3 approximates to -0.995. Now the signal is strongly negative. The thermostat sends a full cool down command. That's the beauty of tanh. It can swing both ways. Unlike Sigmoid, which only pushes outputs upward between 0 and 1, tanh lets neurons communicate in both directions, positive or negative, creating richer representations and helping the model converge faster. But just like Sigmoid, tanh also flattens out near its edges. When inputs get too large, gradients vanish again, making it harder for deep networks to learn. That's why, even though tanh was once the go-to choice, ReLu and its variants have mostly taken over. So, to sum it up, Sigmoid gives probabilities, tanh gives balance, ReLu gives speed and simplicity. Each one shaped how deep learning evolved, and understanding them is key to understanding how neural networks actually think. If this helped you understand things a bit clearer, make sure to drop a like, subscribe, and drop a comment below letting me know what other AI concepts you want to see broken down. Thanks for watching, and I'll see you in the next video.